What's going on, Alex?
Well, Michael, my late calculus teacher Algorithm wanted me to figure out how to solve this differential equation without using calculus. He's dead now, so I figured I'd do it in his honor.
Alright.
But I can't figure it out because I got this line, I've got all these vectors, this field of vectors, but I have no idea what to do without using calculus.
You should use Euler's method.
You mean Euler's method?
Euler.
Yeah, that's what I said.
Check this out. Euler's method is a method of approximation in differential equations. We have here delta y over delta t and your function. What you do is you calculate your slope at each interval. So in this interval, for t delta t equals 0.5, you calculate your slope over each point. And that will give you an approximation of your actual y-t graph.
Okay, I think I get it. So what you're saying is we're taking our initial value and then adding the change of that value according to its slope for an entire interval, which in this case is half a time interval.
That's right.
Okay, but if I'm thinking about this correctly, that means with a concave down graph, we're always going to end up with an over approximation, and if it's concave up, we're always going to end up with an under approximation. Is there any better way to do that?
No, there's no way.
I know a way. Let me show you the Runge Kutta method.
Runge Kutta?
The Runge Kutta method, if you will.
Damn it, Alex.
The Runge Kutta method is an average of multiple lines tangent to the solution. There will be 4 of them. There will be 1 over approximation, 1 under, and 2 weighted. A brief, very approximate calculated or graphical representation of that is shown here. In the Euler's method, you had 1 line that was based on the step size. If you have that 1 line, you're always going to over approximate. The Runge Kutta method calculates 4 different lines. And what it does, it takes the average of those 4 lines to get a more accurate representation or solution to the solution graph. Make sense?
Yeah, I think that makes sense.
We'll go a little bit more into the graphical representation later. But let me show you how to calculate it numerically. The Runge Kutta formula is y of the initial value plus 1 equals the initial value plus the step size of h over 6 times the average of k1, 2 times k2, 2 times k3, and k4. You'll see here that k2 and k3 are weighted because they have a 2 times multiplier in the front, and if you know your average formula, you'll see that this is an average of the 6. Add them all up and divide them by 6. To calculate k1, you use these formulas here. k1 is just a function of t of y. Plug that into the formula, and then each line after that, you plug in the previous line to get that tangent. K2 is t plus 1/2 over 1/2 of h, and y is y plus 1/2 of hk. And you'll keep going down the line. Let me show you with the current problem that you have. Original equation, we have dy dt equals t minus 2y plus 4. Our initial condition is y sub 0 equals 1, and h is our step size is 0.5. K1, we plug those numbers back in and we get K1 equals 2. Taking our Runge Kutta formula over here for K2, we plug in the numbers and chug, we get t equals 1/4, y equals 3/2. Taking those t and y coordinates and plugging them back into the original equation, we get K2 equals 5/4. Doing the same thing for K3 and K4, we get these values here. Taking K1, K2, K3, K4, plugging into the original Runge Kutta formula, we get this math here. It gives us a result of 163 over 96. This is for the first step only. Now we're going to take this number, plug it back in and start the whole second step and get us our second solution. And now, through the magic of video, I'll show you the second step size and math. So with our original equation and our original Runge Kutta formula, we took the equation that we had before, or 0.5 and 163 over 96, plug it back into the Runge Kutta formulas, we get K1 equals this, K2, K3, K4. Taking those in and plug them into the original formula, we come out with 3311 over 1536. And because it's our second step, our t is now 1, and our y value is here. Does that make sense?
That makes good sense. But what does steps mean graphically?
I'm glad you asked that. My friend Mark is going to come in and show you how we do it graphically.
Got your call. And our next step, we'll go through and show what these steps look like when comparing them to the original solution. Alright, now we're going to show you the graphical representation of the Runge Kutta method. You see where before we calculated all of the values for our k's here and plugged them in, and now we've got an approximation for our first step and our second step. And for each of them, we've also displayed each k value that we calculated out for each step, and we've broken them down. But for this graphical representation, we've only shown just the first step because of the complications of trying to graph both the first step and the second step with the k slopes involved with it. If we look at the graph here, we see that our red line here is representing the slope of our first step. We see how closely it's following the actual solution of the graph. In this case, we can now come to the conclusion that the Runge Kutta method really gives a much closer calculation to the solution than the Euler's method that we were using before. Now, how this works in the mathematical area when we were solving, we were taking all of our slopes and then summing them and dividing them over 6 to find the average. Just as I said, we were summing all of the slopes that we have here and then finding the average to bring us a closer value to our actual solution of the graph. Alex, does that make sense to you?
Yeah, I think I understand now. It's like a more advanced version of Euler's method.
Euler's.
Exactly.